In this video, I will be presenting a phenomena of electromagnetism and its use in brushless DC motors. The presentation will be done in two parts. One is this video, and the second one is a report written by Augustas Baginskas. In the video, I will be focusing on particular application of law of electromagnetism in brushless DC motors. At most basic, brushless DC motor is just a bunch of electromagnets and permanent magnets. By Lenz's law, the current flowing through a coil generates magnetic field which attracts permanent magnet. So by switching the electromagnets one after another, the permanent magnet is moved in a circle. Commutation of brushless DC motor, which is just a fancy word meaning the act of switching coils on and off, can be done in a college dropout way by using a switch. But that would be terribly inefficient, so in modern times the act of switching the coils on and off is done by transistors. In essence, transistors are just fancy electronical switches that change their conductivity in correlation to input signal. In general, there are two ways of driving the motor. Simple pulse width modulation way, which is comparable to driving a car while blindfolded and receiving guidance from a guy who does not know how the road signs work, and the field-oriented control way, which basically means that the controlling circuit is listening to what the motor is doing and uses that information to commute the motor more efficiently. Theory of field-oriented control is quite complex, but basic idea of it is nicely explained in the following clip from Great Scott YouTube channel.
Let's draw our sine wave into the space vector diagram, which now takes the form of a circle. What FOC basically does is creating a ton of space vectors whose angle and magnitude follows the outline of our circle. This way we get more magnetic field orientations the rotor can follow, and thus an almost constant torque. In order to create the angle for the new space vectors, all the controller has to do is to switch between two of the already existing space vectors through PWM. And in order to control the magnitude of the new space vectors, we can switch to the remaining two neutral control states that short the coils to one another. This way we can control the strength of the magnetic field and thus the torque. At this point you might think, well, let's just simply apply this PWM technique to the MOSFETs, which will most likely not work out. To understand why, let's take a look at the simplified stator-rotor constellation. At which position do you think it makes the most sense to create a north pole at the top and a south pole at the bottom? Exactly, it is in the middle picture, where the rotor would create the maximum torque, which basically means we need to know the position of the rotor in order to let the current flow through the correct coil. But that is not all, since there will always be a phase shift between voltage and current when it comes to inductances. We also need to constantly monitor the current in order to adjust the phase of the voltage so that we can achieve this perfect pull position. Otherwise, we would get a non-ideal pull on the magnets, which feature an outward pull caused by direct current or flux current, which represents a power loss. That also means that FOC not only offers a constant torque and low noises, but is also the most efficient way to drive BLDC motors.
As we saw in the clip, to effectively drive a brushless DC motor, we need to know a current position of the rotor. This information can be gathered in many different ways, but most often Hall effect sensors and currents generated by electromagnetic inductance are used. To correctly calculate rotor position using EMI, we need to know the inductance and other electromagnetic characteristics of the motor. Fortunately, the ESC that I am currently using can automatically measure these parameters. When characteristics of the motor are known, DSC can now be commanded to spin the motor.